RealtimeSwift will be a SwiftUI style declarative rendering engine for producing real-time video. Here's what we're trying to implement today. I want a fade-in modifier that does picture and sound. So if we have a look down here, we've got .fadeIn is what we want to be able to call, set a duration, an arbitrary real-time source, so that's going to be a video in our case, just playing a clip of my toddler, and so we'll save that for the end. He does some good laughing, and just, you know, it's a small looking thing, but it's actually a huge lot of implementation. So today I'm going to cover three main things. First, talking about how we implement modifiers in a SwiftUI style way. Then we're going to talk a little bit about CoreImage filtering, and then we're going to talk about real-time audio with the amazing AVAudioEngine. So if that sounds interesting, then keep watching. So step one, implementing modifiers. So if you've watched previous videos in this series, you'll have seen me add one modifier just for the environment, but I kind of knew when I came to add the next one, I'd spot a few mistakes. So the first step was to tidy up and generalize the way modifiers work, but I'm going to save you all that details, but just if it looks a bit different from before, that's why. So the first thing we need is this fade-in function. So this is pretty familiar to SwiftUI developers. We just, implement, extend RealtimeView, add fade-in, set the argument, and then that's going to call modifier with our fade-in modifier. So what does modifier look like? Well, modifier is, again, another extension on RealtimeView that returns a modified real-time content that takes the view, the current view, and just associates that with the modifier. And then we've got the types. That's quite simple here in terms of generics. Modified real-time content does some sort of like a little bit of jiggery-pokery here. Modify content, modify body, kind of takes those in and just like calls the body of the modifier, right? So that modified real-time content, right? So the modifier that we passed in, so fade in, we give that we call body on that and we give it content, right? And so that's what we're doing there. Next, we also want to implement resolve on these modified real-time content. So this is how we take a view tree snapshot. And this calls, so we extend modified real-time content. We do some like a little bit of a generics jiggery-pokery, but then we get this modified resolve call that we can call, and that's something that I added recently. So this is doing some stuff to kind of like resolve that into the view hierarchy. So we basically we want to create a tree structure, and we do that with like children basically. So we say we want to end up with a resolved view with that modified content as a child. I'm sort of giving myself some little hints on why I'm doing stuff here, but basically we look for that content and then we call content on that if it's resolvable, which it has to be in this case because it's a modifier, and then we give it a child ID. So that's like just to make sure that IDs are all depending on the position, which is how SwiftUI works too. And then we get that. So we get that. That's another resolved view, and then we add that as a child to this outer resolved view. So that gives us that nesting. And then, so if we go back up to the fade-in modifier and have a look at what that fade-in modifier looks like. So this implements RealtimeView modifier, and actually, like when you call, so that modifier.body call is here, and so that's going to return this kind of internal like fade-in. I mean, they're all kind of internal types, and I'll talk about that in a minute. But that makes a fade-in modifier view, and also passes through that duration. So just a quick note on that, on underscores. So, you might have seen a mismatch of like fade-in modifier view. Like we've got some underscores sometimes, other times not. So the idea is that things that are kind of framework implementation related get underscore prefixes. So basically the further away you are from what the framework users need to think about, the more you're going to see some underscores. And now I'm kind of taking my cues from SwiftUI as well. But so, fade-in modifier is not really something you should ever have to think about from the outside particularly, but I'm not being super strict about this. I'm just sort of feeling my way through it and just sort of trying to give myself cues that, okay, how deep are we in the sort of abstract graph stuff at this point? So fade-in modifier view, which is the thing we just added, isn't actually doing that much, but it sort of just needs this resolve function. We have this modified resolve again, and again it's just sort of like taking that content and kind of like keeping hold of it and keeping that duration, keeping hold of it. So this I think this is right. It feels like an extra layer of nesting, but I think this is right because you've got the modifier and then you've got the thing that it's doing the modifying with. And I think that's right. And then you've got the actual implementation, which we'll talk about next. So its job, basically the real job of this fade-in modifier view, the rest of it is just like tying it all together. But the real thing here is that leaf renderable views get a make renderer function, which can optionally return some instance of renderer. I'd like this to say some. I haven't figured that out yet. It's as like once you get into these generics, it gets like way too complicated for me sometimes. But I'll figure it out. I've been watching all the videos. But yeah, so now we get this fade renderer, right? So not just fade in anymore. Like we're actually going to arbitrarily fade things, and then a target opacity 1.0 and that duration. So now. It's just a note on renderer. So renderer has evolved since we last spoke, and now we have an input parameter into the images. So before it was just like crudely, sticking all the images on top of each other. Now it actually takes an input image or a set of input images so that these render image calls have a chance to actually process images, which is something you need to do if you want to fade an image. But you also see we've got some audio stuff as well, which I'll get into in a bit. So here is fade renderer. It's not called, as I say, not called fade in renderer because we're going to use it to fade out too. So we'll go into that now. So, but first, let's talk about, and we're going to talk about that in a sec. But first, we're going to get onto the subject of filtering with CoreImage. So let's have a look. Right. So what are we doing here? So render image here just basically crudely grabs the first image it gets. It's just literally taking the first one. So I don't know what I'm going to be using connections of those for, but at some point I probably will need to. And then it updates the filter. So it's got, I think, do I show this? Yeah, so we've got this CoreImage colorMatrix filter. But down here you see we're just setting that value of opacity into the right part of that CoreImage filter. We're doing this fade level calculation, which is just a way of like figuring out from when this animation started where we are. It's a colorMatrix filter, and yeah, we just it just takes this 4-dimensional vector, and W is the opacity. And then we just return this output image. We just take filter.output image, and that sort of comes back out. And again, all of these are optional, so anything can happen in this chain. And I'm not 100% sure, but this shouldn't necessarily cause any rendering immediately. I think we're still building up that recipe for the core image. And actually, to verify that, like if we have a look in Xcode and click the, I hover over the result. So I've rendered my full graph at this point, which I'll show you how that works in a sec. But at this point, I can put a breakpoint in and click on the little preview icon, and I get, you get a pretty detailed graph view. We just came from this button here and we sort of expanded to here. So let's have a look. So down at the bottom is our video frame. So this is where we, maybe I'll just start using Spotlight. I don't think I'm going to do. This is what comes out of the video player, and I showed you last time how we get frames out of the video player. And literally, this is like actually an IO surface, which is just some implementation details that we don't necessarily have to think about with CoreImage, and it's coming in a native format. And then it does, it does these little color match adjustments. So it turns Core Media 709 to working space opaque, and then it transforms it to fit to the right size. And then here is where we see our colorMatrix filter, and we can see here is our opacity value, which is sitting in the matrix right there. And then like over here we're sort of doing a background fill of just black, and then this gets cropped to the right dimensions, and then it just like source over combines those two, and that's what composited with is doing. So it just takes the second, takes number 2, takes number 3, puts them together with the right frame, and then combines it with the other stuff. So that ends up making our output image. So I've seen that there's a ton of like detailed core image debugging features that you can turn on as well. So I'm really looking forward to making sure this is super optimized. And the way I was doing rendering in previous projects, you can be using Metal, and using the Metal debugger, but you end up sort of doing a lot of boilerplate yourself. And I like the idea that CoreImages, it's abstracting out some of that boilerplate, but it's also giving you these very powerful debugging tools that Apple use, right? So I like having access to those tools instead of having to build them for myself, or kind of reverse engineer it from the Metal debugger is appealing to me, which is why I'm using CoreImage. So let's now look at how the framework is actually building that output composition. So it's really just this. So we start at the top of our first node in the tree, and then each of these is recursively accessed. So if there's any child, so we check for, so we've got our node, the node that comes in, the top level node of the tree, right? And maybe I can like draw this. So this is node is here, right? So this is our first node, and then we see how many children it's got. And so for each of these children, we're going to call render node on those, and we may or may not get something back. So we're sort of like recursing through the graph and just getting images back up. And then once we've got, you know, one or more images, which is these child images here, then we either just like composite them over each other like we were doing before, or if the node has a renderer, now we delegate that to that renderer.render image and let the renderer do something with it, right? So that's the visual fade. So, you know, we saw, you know, that the renderer is the fade modifier, which just took that input image and applied that CoreImage filter. But yeah, the next subject is audio. So it's now time to talk about real-time audio. So I would love to use AVAudioEngine, which is Apple's audio engine, but bitter experience has taught me that it's just not designed for Mac apps. So my apps like CoreImage Presenter, EasyVJ, it just wasn't. I ended up having to like go against the grain of what it wanted to do. So, you know, I want to be able to access more different outputs at the same time than you can do with AVAudioEngine. So I can do like a headphone output as well as the main output, and sort of target the outputs to the right place without, because what AVAudioEngine tends to do is just like it's basically made for iOS, so it's just kind of wants you to be on the built-in phone microphone and the built-in output, and maybe you can change what those outputs are, but like you know, they haven't really added features for macOS where you have multiple outputs, multiple inputs, and you can sort of get to some of that, but it just sort of gets complicated, and you end up doing these kind of like low-level core audio calls sometimes, and sometimes it's just a bit of a pain. So this, but like if you wanted to just not use the you know, if you didn't want to use a AVAudioEngine but actually dip into core audio, then that's pretty scary too. So you've got all these like, you know, audio component instance new, you've got like this audio unit set property, you've got to like create the audio units by like their component descriptions, which are all complicated. You've got to like do these audio what is it, ASB, audio stream basic description interfaces, like instances, you know, like these are structs that you kind of pass around, and you have to figure out the right format, and if you put the wrong format in, it's just going to crackle. So you've got, it's quite a lot of this is, and it's a lot of initialization boilerplate, and a lot of it's just, I don't really want to be writing that. You know, you also have to pass around these C callbacks, which are all like pointers, and just be very careful not to accidentally call any Objective-C properties or anything else that could make it lock or take too long. But all this stuff, as scary as it is, oh, I've got to know about pointers, you'll notice that if you have used Core Audio, that this is a little bit less scary than it could be, because of these little, we've got some little macros here, audio buffer list silence, or a renderer run, right? That's not Core Audio, that's something else. And this is all thanks to the amazing Audio Engine 2. So, the Amazing Audio Engine was a fantastic audio framework created by Michael Tyson, the creator of Audio Bus and Loopy, nearly 15 years ago. So the original audio engine, or as I will call it, Tai, gave you a node graph like this, where you basically sort of like plugged in, you said, I want a microphone, I want a filter, audio receiver. So you see, like, you know, it's sort of this idea of a node graph to create a signal chain, and like you're plugging in wires like it's a mixer. And this was a fine abstraction, and it's what and basically this framework was retired after Apple implemented their own version of this, called the AVAudioEngine, which basically does the same thing. You see, it's like takes a source file and a player node and a mixer node and an output mode and sends that to the speaker. So it's sort of it's basically the same kind of thing. You can like create these node graphs, but you know, Mike, I as I say, like I didn't really like the like the limitations on Mac OS for AVAudioEngine weren't quite working for me. So in the meantime, Michael hasn't stopped working, and he's actually snuck out the amazing Audio Engine 2, or I think we're going to call it Tight, to save time. And he's taking a very different approach with Tight. So the amazing Audio Engine 2 comprises an infrastructure and a variety of utilities that make it easier to focus on the core tasks of generating and working with audio without spending time writing boilerplate code and reinventing the wheel, which is what you have to do with Core Audio. So this one doesn't give you a node graph, but this concept of a buffer stack. So when I saw this, I was like, it makes sense. Like this, that's actually a much better model for thinking about audio on a computer when it's real time. We don't have to abstract away the reality of real-time audio processing, because when you're doing audio, you're really just processing, passing around these audio buffers. And we're just like trying to make it seem as though we're plugging wires in a studio, but really we're not doing that. We're just kind of trying to, as quickly as possible, get the bytes from one buffer and like do something to it. So I started using Tight a lot. Once I started using it, a lot of my audio problems went away. But I mean, the scary part here is it's in C and Objective-C, not Swift, and I want Swift. So let me show you how the audio looks at the moment in RealtimeSwift. So the main thing you need for the amazing Audio Engine 2, Tight, is an audio controller. Right. So this is my real-time audio controller, and that can have. And in my case, I've just said I'm going to have an arbitrary number of input modules that I'm kind of taking signals from, and then I'm just going to mix them. And so we take that, and basically we make a renderer, which is an A renderer, and that's kind of like the root of everything. Like this is the thing that kind of keeps the audio context and kind of like we pump everything through. We give it an output. In this case, I'm just taking the default output just to see if we can get it working. And then we just we have the modules which we're initializing here, and then assigning it to self, because we want to be able to access these modules from outside, but we also want to be able to directly access those modules from inside the render block. So this is the real-time render block, which has this context, which is, well, yeah, it just takes this context. Oh, you know what? I've missed a new line there. So this renderer block is the real-time thing, and you need to just not do anything dodgy. So everything you see in here is these kind of like C-style calls. It's not, we're not like calling object.method. We are just kind of like calling these plain functions and then passing in like context or the module or something like that. And then we just like start the output. And in CoreImage Presenter, this is all Objective-C, but for RealtimeSwift, I want to see if I can do it in Swift, because there's a lot of boilerplate to the Objective-C approach. And I know that Swift doesn't, has less indirection if you use it right than Objective-C. But the main difference here is how local scope is captured. So this isn't a plain C block, because we're actually capturing modules, right, and accessing it here, right, and that's kind of like the crux of what we need to think about. So in Objective-C, we have this closure, this block that captures these modules. So this is what it looks like in Objective-C. So I'm kind of like making my output modules, and then like updating. This is just, I'm sticking an oscillator into test, but the block has access to like module. It gets context passed into it, but module is coming, well, oscillator. Oh, I don't know how we do it. No, module, I think, is just coming from somewhere. I think I added it to the list. But this context is coming in. But the crux is like when we go from, we basically just see a sequence of C calls in the call stack. And the difference is, right, in Swift, like it can capture these variables from the local scope in the same way, but there's this little sneaky little there's this creepy little this thing here, this thunk for something Corley guaranteed, right? And that's got me a bit worried. Like I don't know if this is going to impact real-time performance yet, so I'm keeping an eye on it. I'm going to implement the audio controller both ways so I can compare. I've got a feeling that I might be able to get rid of this entirely if I use like unsafe pointer wrappers around the local variables. maybe, but I need to do some experimentation. But I also want to keep an eye on it and see if it causes any problems. But yeah, I realized I thought I could just use convention C and pass it in, which I'll show you how I do that for the video audio in a second. But it's not just C, it's Objective-C capturing scope inside a block. So it's a little bit more complicated than just like just sort of abstracting it all away. Anyway, that's the minimal audio controller. But like, so we're just taking a stack of modules and like mixing them and putting them to the output for now. There will be more stuff with that, and I'm going to have like views that do audio stuff. Like the microphone will be like a view in the RealtimeView stack. But these modules that we're talking about here are actually, I've implemented them for cuecam. I'm just bringing them over into the framework, and they're all in Objective-C for now. So if we have a look back at the make renderer function for RealtimeSourceView, then this is the thing that renders the pixel buffers. But now I give the sources a chance to make an audio module. So if the source has make audio module, which it can, or it doesn't have to, but it can, then we can add that module to the audio controller that I just showed you. So an audio module needs to be created with a renderer. So we have to take that renderer and give it to the module, because that's kind of how the context stuff works. So that comes in from the environment. So you see the audio controller is here. That's coming in from the environment. So I'm just like passing in that audio controller at the top into the environment of the graph. So here's our movie source now. So we've got this make audio module implementation, which returns an optional AE module. And what this does is it creates a CC buffer cue player module, which is something I made for cuecam. So what does that give us? That basically lets us enqueue audio buffers from somewhere, so that the framework can then just like pipe that to the output. So where do these buffers come from? Well, they come from, I tap the audio of the player item into the module. So what does that look like? So tap audio is a little scary, so I'll go through it. But this is how you get audio, but this is actually not even that specific to what I'm doing. Like imagine like, as soon as I wanted to play audio to two different sources, optionally to one or the other, like I'm in this world of like C callbacks, and it was pretty scary to have to deal with this just to play a video with AV player, like the most approachable thing in the world. But yeah, so this uses C callback. So I'll just show you how this works now. So we have to, it's gonna like zoom out when I try and like pan. I need to fix this. So what do we need? We need a tap, right? And we do that by doing MT audio processing tap create. So MT is, I forget what it means. This is we do this C call to get this audio processing tap, which we want to add to the player item. So we make an audio mix that we attach to that player item. So this is AV player item. We create this audio mix with input parameters, right? And the input parameters contain that tap that we're going to make, right? A pointer to that tap, in fact, right? So that's, we're sort of adding this audio, setting this audio mix property of the player item with something that is doing a tap. So the tap is initialized with optional callbacks, right? So we're, if we have a look here, we have a set of, so MT audio processing tap callbacks, right? That has a few different options for callbacks. So process, like this process one is the part that like Realtime kind of gets buffers. We've also got to call tap init, and we've got to give it some information and stuff. So here's the Realtime bit. Like this is the meat of it. This is not as slick as I would like, but so we have this tap process which is being passed in down there, right? And this is a convention C pointer that has the right format for that callback specification. So you see your MT audio processing tap, item count, tap flags, and that receives it It receives some stuff, yeah, and then, yeah, so buffer list in out is this unsafe mutable pointer. Oh, it's actually gone off the screen a bit. Let's see. Unsafe, yeah, this is the buffer, right? Audio buffer list, unsafe mutable pointer, right? So to sort of look back at this, let's have a look what we are doing. So our module, we have put into a module pointer, and we've given that to the tap storage down here. And so then when we get that storage here out of the arguments, we take that out of tap by using empty audio processing, get tap storage, and that we can then cast from this opaque pointer to our CC buffer queue player audio module, which is the thing we made before, right? So now we can grab, and then we also need to grab that source audio into our buffer list, and then we can call this function CC buffer queue player schedule audio buffer list into that module. We give it the number of frames and stuff. So that's basically how we're like pushing that through. So here is that CC buffer queue player schedule audio buffer list. Literally just, we've got a circular buffer on our module, a ring buffer, and you see we're not ever accessing that through Objective-C properties. We're always using the pointers and things. So we're enqueuing that buffer list onto that ring buffer, and then it's just like on there. So looking back at our renderer block, we see this all-important AE module process call. Now, the AE module interface defines a process function, which is an Objective-C block type that takes the module as the first argument, this, and then takes the AE render context, which is passed in by the renderer. And here's our buffer schedulers implementation. So this is actually mostly taken from the output buffer module. So that's nice that thanks to Michael Tyson, like, you know, just being able to look at how he's done another thing and then being able to just like adapt that to my needs. It's been really useful to see the source code of that. And this module either uses buffers it received directly or has an audio unit that does the sample rate conversion. And that's what this duplication is about, these two different branches. And really, like, there's also some other stuff going on here where I wanted to actually like debug those audio buffers. I'm not subclassing AE module directly either. I have this CC mixable channel module, which a superclass that I'm using for everything. And then if we have a look here, we see we've got this. This is where we get the stuff that we need to fade, right? So we can set properties on the Objective-C object that can be accessed via the pointer on that gets passed into the closure. So we can still set these properties, but we just never do that on the audio thread. And this implementation of that basically just, it does this AE buffer stack, another like useful utility function from the framework, just to like transition the volume over time to the target volume, and then it keeps that current volume just so it's got some, you see we're passing addresses in just so that it's got a way of iterating on those values, like it's because it doesn't have any state of its own, it's just a plain function call, so we need to give it like somewhere to put the temporary values so that it can do the transition. And then we've got like, you know, I'm doing my metering, and then I'm just like mixing those top, you know, couple of things there. We'll get into that another day. So now for each video frame, I'm calling this update audio. So if we find any mixable channel modules when we call graph.nodes and child IDs compact, if any of these children has well, can do update, so they can all implement. There's a blank implementation of update audio, but if they do something with audio, then that's where they do it. And then again, we're kind of we're looking for any mixable channel modules so that it can. We're sort of like going in deeper. So to find something that needs, if it finds a module that does, if it finds any of these modules, then it will call update audio on that renderer, right? Like so that it can, so basically like, because the you're going to have your modifier here, but then the view, you might have a couple of layers of abstraction before you get to your actual video player file. So it sort of has to go down that tree and find something with audio, and then like takes a reference of that back up and then process it with the renderer of that node. So so that's basically all it's doing. So now our fade modules update audio, just like at the moment it's a bit crude, like it's just setting the target and the current volume. I was having some trouble figuring out why it was silent. Turns out they were both at 0 by default, so I lost an hour to that. But yeah, so at the moment I'm just crudely like setting them both to the same value just so that I can hear it and you can hear it. So it's not going to be smooth transitions, but it works. So that is a 30-minute whirlwind tour around how RealtimeSwift is doing that little fade-in modifier. So I'll give you a quick demo, so be ready to be underwhelmed. So let's see if this works. So you see we've got my RealtimeSourceView. I'm actually not going to give you Harvey. I'll give you Harvey because it's fun, but I'll switch it over to the other one. So I'm going to just implement that. So again, source registry contains, I've just registered a couple of videos into that registry, so just source registry add. So now they're available here by name, and then if I just like run Swift here, we're going to get something very exciting, hopefully. Okay, and there it is. Or if we kind of go back to our cuecam video, we can see, oops, we can see that it slowly fades that in. And I'm just going to mute the app for a minute so that I can just show you kind of my debug stuff here. So I don't even know if we're going to be able to see it all. So you see right here, you know, I've got my little debugging signal. I don't know, maybe that doesn't work in the I haven't really looked at this much in the in Swift UI previews. But you see, this is our audio graph hierarchy. This is our current view state, and you can sort of see that like modified resolve, modified. You know, we can see how that has all worked. Thank you for watching. I made this video using cuecam presenter, and here is what the script that I just used looks like. So I want to end every video just showing you a little bit, break the fourth wall. So I've spent an hour just kind of like putting all these screenshots together with my script so I can look at it on the teleprompter. This is my first run through. I don't want to spend hours producing these videos, but I don't want to just like not be talking about it at all. So it's a bit long, but I think like considering how much I've been through, you can see like we got through a lot of stuff here. There's like 83 cards plus the outro, and then here's my room. I've got the teleprompter there. I've got like my laptop's there, a second screen there. And when I draw with the iPad there, and I've got another camera coming in to show you what this looks like. So you can try cuecam right now, cuecam.app/download, and this is all about making the polish, and you'll have seen some little bits and bobs where it wasn't quite perfect, and a lot of this comes from how I'm currently doing the rendering and the audio in a way that is a bit convoluted. I'm trying to get all of this stuff into a very easy to reason about kind of view hierarchy, like modifiers, get into that Swift UI declarative mindset, and that's how I'm going to just make this thing really good. But thank you for watching, subscribe, etc. Talk about it on Reddit, talk about it on YouTube, and I'll see you soon. Take care. Bye-bye.